Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments, and this is part 5 in a little mini-series within that playlist. And we're doing it on one-way random effects ANOVA models, and in parts 1 through 4 we developed all the theory for and distributions of the sum of squares and etc. And now we're going to do the f-test and confidence intervals for the variance components. So as a reminder, our model is y equals mu vector of 1s, z tau plus epsilon tau are normally distributed. That's the random effects piece of it. Epsilon is normally distributed, the taus and the epsilon are independent. And the f-test of no treatment effect is, the null hypothesis is that the variance components associated, the variance associated with tau is 0 versus that it's not 0, meaning there is an effect. The f-test is this, it's the ratio of it's a chi-squared divided by its degrees of freedom divided by a chi-squared divided by its degrees of freedom. And that's what makes an f-test. And the sum of squares treatment and sum of squared errors are independent. We've shown that, I think, in part 1, but definitely in the little mini series on one-way fixed effects ANOVA. But this is it's an f-test, so this is the mean square treatment, or the sigma squares cancel, and then this is the mean square error, and this ratio is a central f-test under the null hypothesis, and that the numerator degrees of freedom is a minus 1, denominators in a minus a. Now, notes from part 2, the expected value of the MSE is it's an unbiased, unconditionally sigma squared. But the expected value of the mean square treatment is, if the null is true, it's sigma squared. And so under the null, this is 1, and there's no way it'll get in the tail of the f-test, we won't reject. But if the alternative is true, meaning that sigma tau squared is greater than 0, then this becomes large. So then this ratio becomes large, and that's how it gets, that test statistic gets shoved into the tail, and the p-value becomes small. So anyway, a little heuristic development there. Now the confidence interval for the variance component sigma squared, which is the error variance, in part 2 we showed that 1 divided by sum squared error is chi-squared, central chi-squared with na minus a degrees of freedom. So we can put this in a probability statement. So if this piece is chi-squared, then we find the chi-squared value in the right tail. So the area in the right tail is alpha over 2, and then going this way, then the cumulative tail is 1 minus alpha over 2. Sometimes they write this backwards, or not backwards, but differently. They put the alpha over 2 here, and it means the area in the left tail, and then a cumulative they'd put 1 minus alpha over 2 here. And so be sure to note that which direction you're going. We're going from the right, so that's the this value is bigger than this value. So if you keep going from the right, then it's 1 minus alpha over 2, and this probability is 1 minus alpha because the way we pick these values. Now, in this interval here, we solve for the sigma squared. So we divide everything by sum squared error, and then take the reciprocal. When you take the reciprocal, this part becomes the smaller, and then this part becomes the larger. And then this is the confidence interval for sigma squared. Now the confidence interval for sigma tau squared, an exact method does not exist currently. And if we look at the method of moments estimator in part 4, it becomes this. It's actually unbiased estimator too. And then this right here, you can do some manipulations to show that it's really the difference of two chi-square distributions, with weights in front. And an exact method for this does not exist yet, but a few approximate methods exist, and we're not going to cover that in this video. But when we do the R program over everything we've covered here, we'll show you that they do, they'll programs output it, So here, let's look at the covariance, or the confidence interval between this ratio. And this is the proportion of variance due to the between variance. So we know that the sum of squares treatment over sigma squared plus n sigma tau squared, this is a chi-square chi-square random variable with degrees of freedom a minus 1, and then sum squared error over sigma squared divided by its degrees of freedom is also a chi-squared, and this ratio makes it a central F under the null hypothesis. Actually, under the null, and then this is a F with numerator degrees of freedom, denominator degrees of freedom. So we put this ratio in a probability statement. So this right here is what this is, right? That divided by this, the mean square treatment. This is the mean square error, and then we have this ratio right here. And we picked the points in the F distribution that make this probably, the right tail is alpha over 2, and then a cumulative going left, then this is 1 minus alpha over 2. And probably this random variable between these 2 points is 1 minus alpha. So now we start solving for this ratio. And this is what's interesting. So we divide this to both sides. That's what we get here. Now we're just going to call this F2 and F1. Now we take the ratio. So this becomes the least, and that becomes this, right? And then we flip that. Then we took the reciprocal. Now, if this is, put it over this, it's 1 plus this, right? So we subtract the 1 to both sides. That's what this piece is right here. Then we divide both sides by n. That's what this is. And then we're left with this ratio. Now, we take a one-to-one transformation of this. So it's x over 1 plus x. So we put the, if we call this L, and then we take this ratio, and then this, put it in the same thing, x over 1 plus x, we get this. And here we get this. And so that's still probability alpha that this, that this relationship happens. And so this is it. So this is the confidence interval for this between variance. Now a confidence interval for the within variance, which is sigma squared over sigma squared plus sigma tau squared. So from the previous page, this relationship holds, right? This is the F random variable. We just call that F1 and F2. Those are the cut points, in the tails that make this probability true. So then we divide this to both sides, or to here and to here, and then we take the reciprocal, and that's what we get here. Then here we subtract 1 to both sides, but then we divide by n, and that's what these 2 pieces are here. That's divided by n. So we're left with this. Now we add 1 everywhere, right? Because sigma squared over sigma squared is 1, and then this is the previous. Then we skip several steps, and we take the reciprocal, right? So this becomes here, and this becomes here, and it's really just the reciprocal. So then this is the 90, the confidence interval, the 1 minus alpha % confidence interval for the within variance. Well, that's all I have for this video. The next video is going to be one R program summing up everything we did. I think in the mini-series One Way Fixed Effects ANOVA, I did an R program after every video, every part in the mini-series, and I don't think it was well received, so I'm just going to do one program at the end summing up everything that we've done. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.